In this question, we have x squared plus 7x plus 10 over x plus 5. For this entire first page, or at least through the division problems, our goal is to factor all that we can factor, see what cancels, and then list restrictions. So when I look at the numerator, that is a trinomial. I'd be looking for two numbers that multiply to be 10, that add to be 7. Those two numbers are 5 and 2. So this factors into x plus 5 and x plus 2. The denominator, there's nothing that we can factor there, so that's going to stay as x plus 5, and then we're going to see what cancels. I notice that the x plus 5s match, so those go away. So my answer is x plus 2. I don't have to put it over 1. Dividing by 1 doesn't change anything. Now, if I cross off everything from the numerator, then I would. I do still have a restriction, so even though our x plus 5s cancel out, that still gives me a restriction. So x cannot be equal to negative 5. In question number 2, we're working on the same learning target here where we're factoring the numerator, factoring the denominator, and then seeing what will cancel. The numerator factors into x plus 3 and x minus 4. So 3 times negative 4 gives me negative 12, but when we add them, gives me negative 1. The denominator is difference of squares, so that factors into x plus 4 and x minus 4. The x minus 4s match and will go away, so we're left with x plus 3 over x plus 4. With our two restrictions, x cannot be equal to negative 4 or positive 4. So when I look for restrictions, I'm flipping the sign. Even if something cancels, it gives me a restriction. For question number 3, it is one big division problem. So the first thing that I'm going to do is rewrite it and make it 2x to the 4th over x plus 8, x minus 6, divided by x squared, x minus 5, all over x minus 6. Now, I didn't do anything to adjust the problem. I just rewrote it in a form that makes more sense. From here, though, when we divide, we end up flipping the second fraction to make it 2x to the 4th over x plus 8, x minus 6, times x minus 6 over x squared and x minus 5. So now we make it one big fraction and see what will cancel. Because this is multiplication in between, from the start, we can pretty much just make it one big fraction to see what will cancel. So when I look for what will cancel, the x minus 6s go away. And that looks to be about it, aside from this x to the 4th. If we have two x's on the bottom, those will both go away, and this will change to a 2. So my answer is 2x squared over x plus 8 and x minus 5. I also still have to include restrictions as part of my answer. X cannot be equal to negative 8, positive 5, 0, or 6. In number 4, it is multiplication. So again, we're making it one big fraction. We're factoring what we can factor and then canceling stuff out where we can. So again, I'm going to make it one big fraction here and then see what will cancel. This numerator is going to be grouping. So a reminder on grouping is that we split the middle. We see what GCF we have on the left, which is x squared. Left over is x plus 7. On the right, we're going to take out a negative 6. Left over then would be x plus 7. So this factors into x squared minus 6 and x plus 7. The next part, x minus 6 cannot factor. Top right, we can factor out x as a GCF. Left over is x minus 6. And in the denominator, again, we can factor out an x as well. Left over is x plus 7. So I did these very similarly to say that we can't cancel x squared minus 6 with this x minus 6. They would have to match completely in order to do that. Now, when I look for stuff that matches completely, x plus 7s go away, x minus 6s go away, and the regular x. So all of that cancels into x squared minus 6 is our answer. And I don't have to put it over 1, but my restrictions, x cannot be equal to 6, 0, or negative 7. Question number 5, we see that division symbol in between, so I know I'm flipping the second fraction. So we're going to make this 5 over m squared minus m minus 2 times 7m minus 14 over 5. So now we're going to make it one big fraction, cancel what we can cancel, and go from there. So the 5 remains on top. M squared minus m minus 2 will factor into m minus 2. And m plus 1, it's X method, looking for two numbers that multiply to be negative 2, add to be negative 1. In the numerator, we can factor out a 7. And notice how I put it as a times 7 so I don't mistake it for a 57. Left over in parentheses is m minus 2, and then it's over 5. So when we look to cancel all that we can, the 5s will go away. M minus 2s will go away. So my answer is 7 over m plus 1. With our restrictions, m cannot be equal to 2 or negative 1. Notice that this 5 does not give me a restriction. That 5 is just a regular number, which is fine. In number 6, we're going back to multiplication, so we're going to make it one big fraction, factor all that we can factor, and then cancel. For this first numerator, we're looking for two numbers that multiply to be negative 80, that add to be positive 2, should be x plus 10 and x minus 8. That x minus 8 from the denominator will stay. X plus 3 stays in the denominator, in the numerator, excuse me. And then in the denominator, 7 factors out. Left over is x plus 10. We now can cancel all that we can. X plus 10s go away. X minus 8s go away. So my answer is x plus 3 over 7. Including our restrictions, x cannot be equal to positive 8 or negative 10. Again, that 7 does not give me a restriction. In number 7, we're looking to find a common denominator to add those two fractions together. The first fraction is missing the 5n minus 1. Second one is missing the n minus 4. Notice that we don't have any equal signs here. We're not solving. We're just trying to write this as one fraction. So now that we've multiplied by something to get a common denominator, we're going to make it one big fraction. 5n minus 1, n minus 4 are the denominators. Then as we distribute across the top, we get 30n minus 6. Here we have to notice it's a subtraction problem, so I'm going to make this a plus and add the negative directly onto the 6n. So it becomes minus 6n squared plus 24n. We're going to combine like terms across the numerator and make it negative 6n squared plus 54n minus 6 all over 5n minus 1 and n minus 4. So I would want to check if there's any factoring that I can do in the numerator. We could take out a 2, but that would be, I could probably actually take out a 3, but that's about all that we can do from there. So then our restrictions would be n cannot be equal to 1/5 or 4. Now the 4 is the obvious one. We just flip the sign. From the 5n minus 1, it's technically like we're adding the 1, dividing by 5 to get 1/5. Number 8 is the same process. I'm looking to multiply each fraction by what it's missing. So the first one is missing the n plus 5. Second one is missing the 4. So then as we write our common denominator, it is 4 times n plus 5. In the numerator, when we distribute this 2 through the parentheses, we get 2n plus 10. 6 times 4 is 24. So we're left with 2n plus 34 over 4, and then n plus 5. Now we can reduce this one. In the numerator, we can factor out a 2. Left over would be n plus 17. And then we will end up reducing that with the 4 that's in the denominator. 2 over 4, this fraction in front, reduces to be 1 over 2. I don't necessarily need the 1 anymore, so I'm going to leave it as n plus 17 over 2 n plus 5. I have one restriction on this function. N cannot be equal to negative 5. This 4, this 2 don't give me restrictions. They are just regular numbers. All right, finally 9 and 10 on this last page. Now number 9, I have some factoring to do in the denominator first, so then I can see what each side is missing. So I can take out a 3v here. Left over would be v plus 4. So when I look at what they have in common, They share the 3v, but they're missing on the left side the v plus 4. So the left side, we're going to multiply by v plus 4 over v plus 4. So then when we write it as one big fraction, my common denominator is 3v and v plus 4. Across the top, we're going to distribute the 6v through the parentheses. So 6v squared plus 24v plus v plus 1. There's nothing that we distributed to this. It's a plus sign, so I just bring it down. Then we're going to combine like terms and make it 6v squared plus 25v plus 1 over 3v and v plus 4. Now, when we take a look at what our restrictions should be, there are two of them. V cannot be equal to 0 or negative 4. The negative 4 comes from the v plus 4, and the 0 comes from the fact that we have a regular v out here by itself. In number 10, it works very much the same way, where I have to factor this part before I can see what each side is missing. So n squared minus n minus 30 will factor into n minus 6 and n plus 5. I can look to what the other denominator is to maybe give me a hint on what this one might be. They share the n minus 6. The left side is missing the n plus 5. So we're going to make it now one big fraction. N minus 6, n plus 5 is our denominator. Across the top, we're going to distribute this 5 through the parentheses. So 5n plus 25 minus 4n. When we bring this down, making sure to notice it's a minus. We can combine like terms across the numerator, n plus 25 over n minus 6 and n plus 5. Two restrictions: n cannot be equal to positive 6 or negative 5. Onto the back side, we are doing some solving. So notice that on this side, all of these problems have equal signs, so we're looking for an answer. So when I look at what our common denominator should be, we look to the one that typically has the most stuff. So this one's got the most stuff going on, so then I need to multiply the other ones by what it's missing. The first one's missing the x plus 1. Second one is missing the x minus 4. Now we're going to solve across the top. I am going to list my restrictions. X cannot be equal to negative 1 or positive 4. So I know that if either of those answers come up in my solution set, I don't count them. Now we're going to distribute across the top. So 5x plus 5 plus 4x minus 16 equals 7. On the left side, we can combine like terms and make it 9x minus 11 equals 7. And to solve, we're going to add 11, divide by 9. So x is equal to 2. I know that's a solution that will count because it does not match anything in my restrictions list. In number 12, again, we are solving here. This part I do have to factor, however. That factors into m minus 6 and m minus 6. The other two have one of the m minus 6's, but I do have to give each one more, so we're going to multiply each of these fractions by m minus 6 over m minus 6. So I know that if I get positive 6 as one of my answers, I would cross it off and call it extraneous. But now we're solving across the numerator. So we're setting 1, and then this part, I'm going to make it a plus, add the minus directly onto the 1 as we distribute it through. So minus m plus 6 equals 2. Not just that 2, but we have to distribute it through 2m minus 12. When we combine like terms, we get 7 minus m equals 2m minus 12. I'm going to start by adding this m over. So 7 equals 3m minus 12. I add the 12 to make it 19 equals 3m. Divide by 3. m will be equal to this fraction 19 over 3. Now, if you choose to write it as a decimal, that would be fine too, but I know that's an answer that will count because it does not match 6, which is my restriction. All right, in number 13, again, we're looking to see what each part is missing. So I want to look to the one that has the most stuff. So the one that's got the most stuff is this 4p squared. So I want to make everything else look like that. So the first fraction would be missing the p squared, and the last one would be missing 2, because 2 times 2 gives me 4. So then I have a restriction. P cannot be equal to 0. So if that comes up in my answer, I know that I'm going to cross it off and call it extraneous. So then we're setting 5p squared plus 1 equal to 6 to solve and get p by itself. Because I don't have a regular p term and I just have p squared, I'm going to be solving it by square roots. Now, this is not going to be assessed on your test, but it's a good method of solving to review, especially before SAT comes on Wednesday. So to get p by itself, I'm going to subtract 1. So 5p squared is equal to 5. I divide by 5. So p squared equals 1. And then to get p by itself, I take the square root. And anytime we take the square root of a number, we need the positive root and the negative root. Both of those will still count, however, because it does not match anything in my restrictions list. To find a good example of what you're going to see on your test tomorrow, I would look for what we did in the warm-up. That's a good example of solving by factoring. In number 14, again, we have some stuff to factor in the denominator to see what terms we need to multiply each fraction by to get a common denominator. For this middle fraction and the last one, we can factor out a p. Left over is p plus 3. So they all have a single p in common. This one, however, is missing the p plus 3. Before we get too far, I'm going to list restrictions. P cannot be equal to negative 3 or 0. So if either of those come up as a solution, I would cross it off. For this part, when we multiply, I'm going to put this p plus 1 in parentheses as a reminder that I need to FOIL. So when I FOIL that out, I get p squared plus p. That's when I multiply p times p and p times 1. I then move on down to the second half and do 3 times p and 3 times 1. So plus 3p plus 1, or plus 3 rather, not plus 1, plus 3 at the end there, minus 1 equals p squared plus 5p plus 4. So those two pieces, I didn't need to multiply anything by them because they had both pieces of the denominator already. As we solve, I'm going to notice that they already have p squared in common on each side, so those are going to go away. And then as I combine like terms, I'm going to be left with 4p plus 3. Hopefully we caught that. Should be plus 2 when I combine 3 and negative 1. And we're setting it equal to 5p plus 4. Now, as we solve, I'm going to subtract the 4p. Now, if I moved the 5p over, that would be fine too. But I like to solve where the variable is positive. So 2 is equal to p plus 4. We subtract 4 to get p by itself. P would be equal to negative 2. And again, that's a solution that would count because it does not match anything. If it did, I would cross it off and we would have an extraneous solution. Finally, in question number 15, again, we're doing the same process here where we're looking for common denominators before we can solve. So I typically want to look to the one that has the most stuff going on. This one is GCF factoring. They each have a p in common. Left over is p minus 5. So I'm multiplying each part by what it's missing. This part's missing the p minus 5. This part is missing a p. My two restrictions, p cannot be equal to 5 or 0. And then we're going to see that we FOIL in the numerator. So p squared plus p minus 5p minus 5 equals p plus 1. And now we're going to combine like terms on the left before we do anything else. We're going to make this p squared minus 4p minus 5 equals p plus 1. Now for this one, we're going to end up factoring it to solve because we have this p squared and p term where the p squareds aren't going to cancel. This is going to be trinomial. This one will be a very, very good example of what you're going to see on your test tomorrow. So I'm going to subtract p on both sides. Also subtract 1. We have to make sure it's equal to 0 before we can solve. So then we're left with p squared minus 5p minus 6 equals 0. So I'm looking for two numbers that multiply to be negative 6, add to be negative 5, should be p plus 1 and p minus 6. So positive 1, negative 6. When I solve, I flip the sign. P is equal to negative 1, positive 6. Because neither of these match my restrictions, both of them will count. All right, so we're first going to take a look at the key features of these two graphs. Now I'm going to have to do a little bit of scrolling back and forth, but I'll go ahead and fill them in as we go. So the first thing is holes. Holes are any open circles that we have, and we're going to list their coordinates. So the holes of the first graph is at 4, 2. Vertical asymptote is the one that goes straight up and down. It starts with x equals. This one is at x equals 3. Our horizontal asymptote starts with y equals. This one's at y equals 1. We have an x-intercept located at 2, 0. Now when we get to domain, we're going to have to break it up into pieces. So we move from negative infinity to 3. We move from 3 to 4, where our hole is located. And finally, we move from 4 to infinity. Now our range is going to work the same way because we have that hole that's going to break it up. So range goes from bottom to top. I go from negative infinity to our asymptote at 1, from 1 to the hole at 2, and then finally from 2 to infinity. The last thing we're looking at is end behavior, and that's talking about the direction that the endpoints are going. So as x gets bigger and x gets smaller, our y values are never going to cross positive 1. Notice how that matches our horizontal asymptote. All right, now looking at the second graph, we've got one with a little bit different shape, but still the same key features that we're finding. So first on holes, that's none. There are no open circles there. For this graph, there are two vertical asymptotes located at x equals 1 and x equals 4. We have one horizontal asymptote located at y equals 0. As we get to x-intercept, this one is none. That graph never crosses the x-axis. Our domain is broken up into 3 pieces because we have the vertical asymptotes there. So it moves from negative infinity to 1, continues from 1 to 4, and then finally from 4 to infinity. Our range is broken up into 2 pieces from negative infinity to 0, and then from 0 to infinity. Our endpoints are never going to cross at further than 0. So as I look at end behavior, the right side and the left side are never going to get any lower than 0. So now we're taking a look at what these would be if we were finding them algebraically. Now I'm still going to go in the order that we usually did. So first thing we would find is the horizontal asymptote. So these are the same when I look at the ratio of the degrees. So it's x squared over x squared. So that's taking the ratio of the leading coefficients, which is 1 over 1 or just 1. The next thing that we find is the y-intercept. Y-intercept occurs when x is 0. So if I put 0 for both of the x's, or all of the x's rather, all those terms with zeros will go away. And I'm left with negative 3 over 9, which reduces to 1/3. And as a coordinate, that's 0, 1/3. For everything else, I need to put this in factored form. So the numerator would be x plus 3, x minus 1. Denominator would be x plus 3, x minus 3. So I know that x plus 3 will cancel, giving me a hole at negative 3 something. So continuing on here, I know the hole is at negative 3, so I want to put this back into the simplified version of the function, which is x minus 1 over x minus 3. So if I put negative 3 in for both of the x's, I've got negative 4 over negative 9, which is just positive 4 over 9. So the next piece is vertical asymptote. That comes from anything left over in the denominator. Anytime I have a factor, I flip the sign. So that's at x equals 3. X-intercepts are left from anything in the numerator. Again, I flip the sign. I write it as a coordinate 1, 0. Moving on to the second one, again, we're going to start with horizontal asymptote. This one is bottom heavy. So if it's bottom heavy, it's y equals 0. Then moving on, I'm going to find my y-intercept by putting 0 in for all the x's. I know that those will go away. And I'm left with -4 over -28, which reduces to 1 over 7. And as a coordinate, that's 0, 1/7. Then I'm going to go ahead and factor. So x minus 4 over x plus 7, x minus 4. I know those x minus 4s will go away, leaving me with a whole at 4, then something. The function I have left over is 1 over x plus 7. So I'm going to go ahead and take that 4, plug it in for the x that I see. So the y coordinate of the whole is 1/11. Vertical asymptote comes from anything left over in the denominator. So this one's at x equals -7. X-intercepts would be none because there are no factors in the numerator.